Yeah, today I talk about for the 3 plus 1 form of the general relativity MHD equation. So until yesterday, so we give to the Newtonian MHD equation, and then yesterday I give to the concept of the special relativity and the general relativity. Based on this today our lecture, then so I hope that please. Yeah, I hope you can get in for some concept of the why using for this 3 plus 1 format to using for to solving for the general relativity MHD equation into the computer. Okay, so first, this is a general relativity hydrodynamics equation. So unfortunately, I directly jump into this equation. It doesn't derive to this one. So general relativistic hydrodynamic equation are obtained from the local conservation law of the stress energy tensor. Stress energy tensor T mu nu, and to the matter of the current density J nu. This is coming for the continuity equation. So we have a hydro equation. We have just 2 equations. So this is the nabla mu is a rho u mu, and then to the nabla mu the T mu nu equal to 0. So this is a continuity equation, and this is the energy momentum equation part. It's so the conservation of the energy momentum. It's come to there. So in the general relativity, we are using for this is the nabla mu. It is a covariant derivative. This is associated with the 4-dimensional space is a metric. So now we are writing for the Greek letter to this mu is coming from the 0 to the 3. So 0 means to the time, and the 1, 2, 3 is the space. So this is the 4-dimensional. It's written to here. Then so if you think about the density current is given to the J mu equal to the rho u mu. So this is to the above for this kind of equation. So here, u mu is also the fluid flow velocity, and the rho is the rest mass density in the local inertial frame to there. Okay, so here I can give to some example of the energy momentum tensor. So the energy momentum tensor, sometimes we say the stress the energy tensor. For here I show about for non-perfect fluid is defined out here. So this is yesterday, every time I give to this is the perfect fluid case, but I only, the guys also doesn't come to here. So I try to give, yes. I want to give this one at one time, but unfortunately he's not coming here. Okay, so this is the non-perfect fluid case. So this is T mu nu. It's a normal rho the plus 1 plus epsilon. This is the u mu u nu, and then including for this mu theta. Yeah, this is the internal. Yes, this is the epsilon is the specific internal energy. For the fluid, P is the pressure, and H the mu nu is this is a spatial projection tensor here. So this is getting for the u mu u nu plus the G mu nu, and in addition you can add to the mu and the eta is this coming for the shear and the bulk viscosity is the coefficient, and also including for the expansion of the theta. So this is the fluid, and also we can also put onto the heat flux onto this here. The energy flux part is also coming to here. So this is the fluid decomposition writing for the non-perfect fluid case. Then this is including for some expansion of the mass and also some shear and the bulk viscosity component, and then spatial shear tensor is also calculated for this kind of way.
Sorry.
Yep.
The theta term is the covariant derivative of for velocity.
Which one is
Theta.
Theta is here.
It's the.
Oh no, it's
yes, this paragraph.
Yep.
No.
The covariant derivative of velocity. Yes, it is.
Yes.
Sure. Thanks.
Okay. Yes.
It's written there.
Yeah.
This is the hydro.
Yeah. This is the yes. We say this is the hydro energy momentum tensor. Doesn't worry about any magnetic field, but later. So first I can talk about for the general relativity hydrodynamics, then go into there. This is the most complicated state. I just using for the mostly in the following we will neglect for the non-adiabatic effect. So it means such a viscosity or heat transfer or energy it's just neglect. Then the energy momentum tensor is given to only for the perfect fluid. This is written to the rather simpler. So rho h u mu u nu plus the gas pressure. So this is a relativistic specific enthalpy. So this is 1 plus epsilon to the p over rho. It's included here. Then the general form to the energy momentum tensor is written to like this. So the T mu nu this is a 4x4 component including here. So T00 component, we say this is the energy density, and then T10 to the T0, this is the momentum density, and this is getting for the energy flux, and then this diagonal term is making for the isotropic pressure, and then left over to this is momentum flux. So T mu nu is also including for to this 4x4 metric information, but this each component have some the meaning of this one. So this is coupling fluids. Okay, so this is general relativist magnetohydrodynamic equation. So the general relativist hydrodynamic equation plus Maxwell equation. This is same knowledge, same way to into the Newtonian MHD case. So this is starting from the continuity equation plus the conservation of the energy momentum tensor and add to the Maxwell equation part. Where this F mu nu is a Faraday tensor. So maybe this is construct from the electromagnetic field. This is E and B as a median is the general frame. This is curl U is out here. Then this is calculated this kind of way. So the Faraday tensor, I think yesterday I can explain to this one. So the normal Maxwell equation to starting for the E and B, it doesn't apply for to the directly, it doesn't apply for to the relativity case. So every time we need switching for to the Faraday tensor. Then this is a Faraday tensor including for to the electric field and the magnetic field is mixed up together. So this is eta is a full antisymmetric is the symbol, and the G is the determinant of the 4 metric. And then so the dual Faraday tensor is also this is a duality is coming to here. Maybe you can compare to the B, it's changing for the E or something like this. Then the ideal MHD limit is coming from to the F mu nu, the U nu, it's just equal 0. So this is the same ideal MHD limit because the current is written to this constant. And then this sigma equal to infinity. This is just drop off, so it means that this is going to 0. Is one of the condition of to the ideal MHD limit is come to there. Okay. So any question something?
No, you are not making any assumptions about the magnetic field configuration. No force-free condition.
Yeah.
No.
Yes. This is a rather general situation, and the important thing that we are put on the generic frame over there. After that, this
without magnetic resistivity.
Yeah. Okay. So the resistivity is of course including here, but my talk is just ideal MHD. I don't put onto the resistivity.
Sigma goes to infinity.
Yep.
The
Okay.
electric conductivity goes to infinity.
Yeah. So to eliminate this electric field from the equation, so it is convenient to introduce a vector in the fluid frame. Then the electric field in the magnetic field, its 4 vector, it's written to like this. So using for to the Faraday tensor, the dual Faraday tensor, and then this equals 0, and then this is U mu B mu equal to 0. This is the ideal fluid, ideal MHD limit is coming for this constraint to there. Because going to the fluid frame, we cannot see above for the electric field. So we just say above for this is equal to 0 to there. Then so the Faraday tensor is using for it written to this we can see above for this kind writing over there. So this is the small b is including for this one, so we can rewrite in for this one. Then energy momentum tensor in the ideal GRMT case, it's given to this kind of the equation. So, yeah.
Please go back to the. Okay, here.
This one? This one?
This one.
Yep.
Okay, we are in the ideal MHD limit.
Yes.
Which is we fulfill this condition.
Yeah.
Here.
That's fine. Yep.
Let me see the dual of the Faraday tensor because now because in the next slide
Yep.
you are going to use the dual. Of
Yes,
the
duality
Faraday
here. Yes.
To get the 4 vector for
Yep.
right. So could you please go back?
Yeah, this is the simpler. So this is our definition of the magnetic field. It's getting for the dual magnetic field times the U.
Right.
Then this is the breakup for this is U is going to there. So this is written to this kind of equation. Then, yes, this is the energy momentum tensor. So important is the magnetic field contribution coming from this b square. This is the small b square plus this is the pressure position is also coming for this is half b square, and then after that also magnetic field includes here. So this is the addition for the compared to the energy momentum tensor in the hydrodynamics and the energy momentum in the general analysis magnetohydrodynamics case.
Yes, you have the tension term and
Yep.
the
Pressure term, yes. Yep. This is divided. Then this b square is of course this is b mu b nu. This is the calculation to the covariant variable and the control variant variable is calculation there. Then this is the square. The fluid frame, the magnetic field strength is, if you think about this is large capital the spatial magnetic field or electric field, this b square is just going to the b square minus the e square relationship.
So it gives directly the pointing flux.
Yes. So this is a similar things because if you see about for the Newtonian case, so electric field component is coming to this calculation here, but now we are because magnetic field and electric field it's if usually we can define to an Eulerian observer, but this magnetic field is getting for the fluid frame because the density, velocity, or some pressure is given to the fluid frame. So we need to have a mix up for the fluid frame. So it's not looks nicer. So we are everything this magnetic field and electric field is going to jump into the fluid frame. Then we can redefine it. Then this energy momentum tensor is much more similar or easy to understandable the way to return to here. Yes. Oh, yeah. Okay, maybe yes.
In this form, are you assuming the divergence of the magnetic field equals 0?
Yes. So this is a big question. Yes, we are starting for the idealmetry limit. This is the assumption to get in for this one. So if you think about for the resistivity, including here, we doesn't use it for this small b, the for magnetic field.
No, but anyways, the divergence of B will be equal to 0 even in the resistivity.
Okay. Sorry, divergence b equals 0 equals, yes, we need. Sorry, I did it mixed up. Idealmetry, not this. Yeah.
But anyways, B squared is still in the fluid, right?
Yes, yeah, this is a fluid frame. Yes.
It's still in the fluid because this is the 4 vector.
Yep. This.
And it's giving the pointing flux in, but is the B squared.
Yeah.
Right? This is in, let's say, this is in
Yeah, because the b square is the energy, so we know about for the energy flux, right? This is just think about it here. Yeah, b. Yeah, sorry.
The total moment tensor
Yeah.
is conserved.
Yeah, this is conduct, yes.
It is divergence-less because
Yeah. Hmm?
they are synchronous. But what happens is the components. When you write the energy moment tensor of the fluid, do you assume that it is separately
Yes.
conserved?
Yeah. Later we can talk about for this equation. It's separate with the momentum equation to the energy equation. This is similar to the Newtonian analogs.
Yes,
This
but
no, but
the
here we have
fluid,
everything together.
we have a perfect fluid.
Yeah. This is yes. We assume it for the perfect fluid because yeah, you missed my part of this one. This is starting for the non-perfect fluid. This is the written to here, including for some shear viscosity or some expansion something. But my talk is everything just is neglecting for this non-additive effect. So this is a
No problem.
Yeah.
If it is a perfect fluid,
Yeah.
or if it is an imperfect fluid, it doesn't matter the
Yeah.
question because in general, when
Yeah.
you have, for instance, a mixture. Here is a magnetic is an electromagnetic field plus a fluid. In general, for instance, in field theory, we should have a Lagrangian of the system, describe the particles, describing the electromagnetic field, and describe the interaction. And from this Lagrangian, you obtain the energy moment tensor.
Yeah.
some degree of freedom here, because we are assuming that, okay, I have the energy moment tensor of the fluid.
Yep.
I have the energy moment tensor of the field,
Yep.
of the electromagnetic field.
Mm-hmm.
The divergence of the total energy moment tensor
Yep.
is 0,
Mm-hmm.
but I don't know how the interaction between particles and charge
Yeah, that
in the
yes,
field
yeah,
is being described.
yes. This is the yes. So this is yeah.
the same approach for Newtonian.
That's right. Yes. So we are concerned about for this is fluid approach. So it means that we are just only think about for the macroscopic picture, not that doesn't including for the any interaction between to the particle, so electron and ion, and also the electron to this the magnetic field or electric field both.
Because in general relativity, if you suppose that they are coupled only by gravity, and then the energy moment, the divergence of the energy moment tensor of the fluid is minus the divergence of the energy moment tensor of the electromagnetic field, in such a way that the total energy moment tensor is conserved.
Yep.
But in general, it's not clear, at least in this macroscope. For that reason, I ask if you know some Lagrangian approach
To get info here.
to this system.
Okay, so this is I don't know. Usually this is similar to the Newtonian approach. We are starting for to the Boltzmann equation into the GR way, and then this is getting for the momenta, and then to deriving for to this fluid equation. So this is everything straight is similar to the Newtonian way to there. So the Lagrangian is also this is mixed up the particle thing, but this is the particle is also different to a little bit fluid case. So this is fluid also. We think some assumption is already including for to the without this microscopic picture, everything going out. This everything is one of the bulk of the fluid, to including for the magnetic field is affected over there. So I think something we are missing up also. Yes, but this is our approach.
Can I make a comment on this? When you integrate the Boltzmann equation to get the fluid approach, you put on the right-hand side the collisional term, and you make this collisional term equal to 0 because when you integrate the distribution function over all the velocity space, you are already taking into account this microscopic average interaction between the particles in each position and in each time, right? So we integrate the Boltzmann equation, the distribution function over the space, over the velocity field of the particles in the microscopic world. So we get averages of these interactions, of these collisions between particles of different charges and with the neutrals, etc., in the microscopic level. What you may ask is, but what is the distribution function? Because when we integrate this distribution function, we get the moments of the distribution function that are the macroscopic variables like density, the average bulk velocity in each position and time, and the temperature, etc., the internal energy, right? What you may ask, if these equations are missing any collisional term, when you integrate the distribution function over the velocity space on the right-hand side, the collisional term of the Boltzmann equation, right?
Yeah, but this collisional term takes into account the electromagnetic field?
No. These are external forces that are on the left-hand side. And when you introduce this force there, you are already introducing this force over that collisional, over those average interactions that you calculated in the microscope. So think about the Boltzmann equation.
Yes, but if
The
you
Newtonian
are supposed
relativistic
that there is a perfect fluid,
Yes.
and then
the right-hand side
is zero.
is 0 because it's a perfect fluid. If it's a viscous fluid, etc., then this right-hand side, you introduce this collision, or you integrate over them, and then you have the diffusion coefficients, right? Like viscosity, resistivity, yes, the shear terms.
Oh, my only point is that it seems that the degree of freedom of the fluid are in some way unconnected with the degree of fluids with the degree of freedom of the electromagnetic field. Because here we have a mixture of is a fluid in the presence of the electromagnetic field. Of course, it is electrically neutral. Microscopically, it is electrically neutral, but the motion of the plasma is
you do take into account in the kinetic level. So when you go to the fluid approach, you are already assuming that this averaging has been performed in the microscopic level. So this is a complete fluid description. We are not missing anything as long as, you are right, as long as the fluid approximation is correct. Not always is correct. So for instance, if you have to study particle acceleration, you have to go back, recover the kinetic theory, right? We can discuss this later with the Boltzmann equation.
Yes, please.
But I think that this point is very important for all the students as well, right? To have this
my point is that in a formal, in a self-consistent Lagrangian approach, we should have the Lagrangian of the particles, the Lagrangian of the field, and the Lagrangian of the interaction.
But
And
this is
with
what
this,
you do
we
to the
obtain the energy moment tensor for all this system.
But that's correct. But this is what you do in the kinetic theory approach. We are in the fluid approach already. We have integrated over the velocity
I'm
space.
thinking I'm not talking about kinetic theory, because from the Lagrangian, you obtain directly the energy moment tensor.
But then, if you start with the Lagrangian, then you have to describe correctly all these interacting terms that the kinetic theory, when you move from the kinetic to the fluid theory, you are integrating over the moments of the distribution function. So this is statistical mechanics that allows us to get a fluid description. We use statistics. And there is, of course, you can always look for a Lagrangian formalism in order to get this. But I think the easiest way description is do this integration, this statistical mechanics analysis, and integrating over the distribution function in the kinetic theory to get the macroscopic fluid. It's a different formalism, right? But it's a fluid formalism. It's an approximation, right? A macroscopic approximation, right?
Oh, yes. But
Yeah.
my problem is
We can discuss this later.
Yeah. Okay. So this is important. The energy momentum tensor is including for the fluid part and the electromagnetic part. This is the addition to the MHD part. So the formally we try to a little bit. Yeah. So this is a transformation between this is the small b nu and the capital B nu. It's capital B nu is the normal is a 3 the magnetic field, and then the B mu is this is we say it a 4 magnetic field into fluid frame. So this is our transformation from to the B relative for this one, and then B0 is with the time component is written to here. B nu is a provided evolution equation of the magnetic field. It's written to this kind of way. Then the time component of the Maxwell equation lead to the constraint. Then the scalar of the B square is also calculated here. So this is some mathematical calculation based on the small b to the capital B. So this B square also including for even for this is three space component, you need to the control variant covariant calculation to include. So this is the conservation law up to the general relativity MHD equation. So it's respect to the explicit coordinate chart of the x mu is that this is x0 equal to t and the xi equal to 3 spacetime. So this is the continuity equation, momentum, and then the Maxwell equation is come to here. So where the scalar x0 represents to the foliation of the spacetime with the hypersurface, it means to the x, it means to the time. And then where the g is the determinant of the g mu nu, and then this is the capital the lambda mu nu. Lambda is this is the Kirchhoff symbol. So this is just coming to here. So important point is here. Symbol is coming for the energy momentum tensor. This is related for some the curved spacetime correction term. Come to here. So the closing for this is similar to Newtonian analog. So we need closing up to this is equation using for the information of the equation state. So that it's relating for the pressure to some fundamental thermodynamic quantity like this, the pressure density or internal energy, something like this. So that we are using for the two type of the equation state. One is the either in conjunction with Einstein's equation. Also, the Newtonian analog is similar. This is Euler equation plus the Poisson equation to calculate for this system. But just avoid this solving for the Einstein equation. Just consider for this test fluid approach here. Okay. So the solving for this MHD equation. Yeah. 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 Degree, yeah, I think degree of freedom, yes, I think so, yes. This is a similar polytropic equation, yes. Polytropic number, I forgot the constant.
Yeah, no, it's related to the degree
yeah.
of freedom.
Yeah.
The hypothesis of
This is same as yes.
maintain the same local equation state.
Yep. Yep. Okay, do you have a question? No? Okay. So is going to the solving for the general relativity equation on the computer. So general relativity states that our world in the 4D and then into the curved spacetime, and then general relativity image equation also describe its dynamics in the 4-dimensional curved spacetime. So showing the numerically. This is the concept of the flowing of the time. So time is just one of the dimension and on the same level as the space-time also. So there is a successful approach is using for the 3+1 formulation. We need divide to the time and the space-time. This is differently. So later I can talk about for the what a 3+1 formalism to there. So this is the first about for foliation of the 4-dimensional space-time. So the concept of the 3+1 formalism. So space-time is foliated with a set of the non-intersecting space like a hypersurface. This is right into sigma. Within each surface, so distance are measured with the spatial 3 metric. So using for the 3 is the gamma, we say that gamma is a spatial 3 metric. And then time-like unit is a normal vector to the hypersurface. It's right into here, so n mu. And then this is including for to the alpha. It's also is a tangent up to the t. Yeah, derivative, yes. Nabla mu to the t. Then also we see have some normalization condition to also get into here. Here we are writing for the alpha is this is lapse function, and then to the omega mu is the direction of the time. Then so that n mu is just only for the minus alpha to the space component becomes 0. So because everything only for the time like. So observer moving with the 4 velocity n nu is called the Eulerian. So we are making to the Newtonian analogy. So that we consider about Eulerian observer onto this system. Any vector, so B mu, may be projected into temporal component using for the time like unit normal vector, and also consider about the spatial component. This perpendicular, this is the projection using for any vector to there. Then, so that we are also writing for the 3-dimensional spatial metric associated with each hypersurface. Also consider about for this is the projection of this normal for the metric to making for this kind of way. This is the 3 spatial metric. So this analog is simpler. We are thinking about for one of the hypersurface. Then this is n equal to the perpendicular to this is the vector to onto the completely time-like unit to consider there. Then all this the metric or all other quantity is just divided to the parallel to the time and the perpendicular to the time to making for the space and time. We can just divide it. Okay. So this we must ensure that when going from to the one hypersurface the sigma at the time equal t to another sigma at the time t plus delta t, all the vector originating from the sigma t and end up to the sigma t plus delta t. So that we must onto the single hypersurface every time because our simulation is getting for the one time space, then going to the next time step. So the all quantity is updating for the next hypersurface plane. If it doesn't onto the same single hypersurface, this is broken up for this assumption. So the most of the general such of the such vector that connect to the two hypersurface is, so T mu is alpha n nu plus the beta mu. Here, the beta is n is a spatial shift vector. We say this is only for the the spatial component, and this is completely perpendicular to the time-like normal vector. And the unit vector component is also written to this kind of way. So here we are writing for some analog here. So this is the one point of the simulation. Try to go into the next time step to here. But this is coming for the first. It's the shift the Laps function to including for this along to this perpendicular to the hypersurface. We can go into up to there. Then we need making for some shift to the additional moving of the position to get in for this shift vector to part. Then we are generic right element. This metric in the 3+1 decomposition is made for the like this. So the GTT term is including for the alpha square minus the beta I, and then also including for the some the orthogonal term is just only given to the spatial 3 metric, and then orthogonal term is coming for the some beta correction. We say the simple 3% decomposition of the metric part. So when the beta I equal to 0, so it means the dxi, the Laps measure to the proper time d tau between the two adjacent hypersurface position. So this is given to the time, which is related for to the Laps function. Then shift vector is measured to the change of the point from the two hypersurface. So this is getting for this one. Then, so spatial metric measures the distance between the point onto the hypersurface to there. Okay, so this is the meaning of the relative of the alpha. That is the Laps function. Beta is the shift vector, and then a spatial metric to there. Okay. So this is a covariant contravariant metric can be written to here. So this is the 4 metric. It's written to like this. This is the covariant metric and the contravariant metric term. It's written here. And also, we are using for this is the determinant of the G. The metric is also related for the alpha time to the determinant of gamma. Determinant gamma is the same as the determinant of the 3 spatial metric to gamma. So to here. Okay, so this is a similar calculation. Okay, so now it's considered for the spatial for velocity. So special for velocity v is measured by the Eulerian observer is given by the ratio between the projection of the four velocity u into space orthogonal to the n. It means the spatial component. So getting for this one. So this is a spatial component I, and Lorentz factor of the u as measured by to the n. So this is minus n mu u mu. It's getting for the alpha ut. This is also related for the Lorentz factor in here. Okay, so this is a spatial the four velocity is measured by the Eulerian observer. It's written to here. So of course, velocity is this is three component. It is only for the spatial component. So time component becomes 0, and then spatial component is calculated for the like this. So mix up for the alpha and the ut over the ui over ut plus the shift vector. So it's there. Similar to the this is a control variant component, covariant component also mix up to like this calculation. So here using for the this is u mu u nu is a normalization constraint. This is alpha ut is going to the this kind of calculation. It means the w is a Lorentz factor. So usually Lorentz factor writing for the gamma, but the Newtonian numerical relativity guy mostly using for the w is the Lorentz factor. So sometimes this is misunderstood. So it's writing to here. Then so the rewriting for the spatial for velocity is also that this is and this is spatial 3 velocity. It's the ui over to the Lorentz factor plus this is beta over to alpha. This is also correction to come to here. Then so that sometimes you can write in for the transport velocity. So transport velocity is ui over ut. This is getting for the alpha bi minus to the beta I. So this is some correction of the GR term is coming to here. Okay. Yep. Yep.
A question here.
Yes.
Because in general, I mean, depending on the general relativist code, the output
Yes.
of the calculations
Mhm.
is not necessarily v.
Not necessarily b. Yes. Yes. We note about for the alpha and the beta, and then we can also calculate the Lorentz factor. So any kind of the velocity like this, a 4 velocity or 3 velocity, or mixed up for this one, doesn't matter. We can after that we can calculate anything.
Yeah. But we must know.
Yeah. So the of course must know to the relationship. This is the usual relationship. Yes.
All the possibilities are here. That's true.
Yeah. Okay. Yeah.
When you have a fluid, the fluid may work like a support for the observers.
Mm-hmm.
And then, for instance, in the Eckhart formulation, you may go with the particles of the fluid.
Mm-hmm.
And this work is in general. But it's not clear for me. When you introduce the 3 plus 1 description, it seems that you cannot write, you cannot choose the form velocity to be commobile with the fluid particles.
Okay.
In such a way that the fluid is
This is
But
yes.
u is co-moving.
No. This is Eulerian observer to frame.
No, v.
B is B is yes co-moving velocity. Yes, this is the fluid velocity. It means
the natural choice should be if you are comoving, then the form velocity is delta of mu 0. We don't have a spatial velocity.
yeah. So this is yes.
How will he cover this?
This is it's changing for the observer, right? So I think it's for the Eulerian observer. So it's almost moving. This is the first my lecture. So this is Eulerian observer. Just see about for the sitting, show about for the how to moving for the fluid. But if the co-moving frame is jump onto the velocity onto the fluid velocity, then we can see the. So between the changing, it's just only to the Lorentz transformation. You can try to do that. So just space and then solving for the numerical solution of the observer. Like this, we think about the law, or there. Composition, that's it. So this is post-processing. So the one, this is one of the hypotheses on there. Then converting for to the transform to and the, for the general relativity radiation, or making for some radiation, how to make there. The Eulerian observer, yes, this is the, I want to say that. So this is the fluid line that we are making for the fluid is follow to this one. And then this is the timeline. This is the coordinate time is also the doesn't straight line. Of course, this is the GR. Then we are consider for the Eulerian observer, it's just only for this parallel to this each point over there, up to the next hypersurface. So Eulerian observer at the rest of the hypersurface moving from to the sigma t to the sigma delta t, along with the normal unit normal vector speed given by to this one. So this is just only to there. So it doesn't follow to the fluid line. It doesn't follow to the coordinate line. This is every time it's perpendicular. Normal vector just follow to this one. Then we need correction to making for the shift vector to changing for the position. Now we are now explaining about for the how to decompose and also what's the observer meaning of decompose the metric and the meaning of the this Eulerian observer. Then now we are touching for to this general relativity immediate equation now. So that we try to develop for the 3+1 formalism of the general relativity hydrodynamic equation. This is easier first. Then so the first consider about for continuity equation. So this is the continuity equation is a 4-dimensional written. Then we can rewrite in for this one. But this is also see we including for to this mu. This is the 4 component 0 to the 1 to 3. Then we can divide to this one to making for the t term and spatial term. So this is at this based on to this is the continuity equation. This 3+1 decomposition is very straightforward. Just doesn't have any additional calculation. And then so the conserved variable is here. So this is minus rho u mu u nu. This is writing for the rho alpha ut, or sometimes we are writing for the rho times the Lorentz factor. So this is the conserved variable to come to here. Then rewriting for the discontinuity equation to using for this t. So this is the time time derivative to getting for to the d plus a spatial derivative plus this is a d plus is a d bi. But this is comparable for to the Newtonian case. We are see about for to the this is the determinant square root of the determinant of gamma. This is coming for the correction of the GR, and also the this is the bi is getting for the some transport velocity type of things. This is also correction about for the alpha and beta of to the velocity part. Yep. Okay. Yes.
It's not clear for me.
Yeah.
The physical meaning of the transport velocity. Is the transport velocity the velocity measured by observer at rest with respect to the coordinate grid?
Yeah.
But this observer is the observer in an arbitrary position in the coordinate grid, or in the same position of the fluid that?
Yeah, this is the same position to get in for to this alpha and to the beta, because if you think about for to the special relativity, we don't have this kind of thing. So if you this is jumping for the special relativity to general relativity, so we can get in for this kind of correction it's come up. So it means that this is the space-time variation.
The amount,
Yeah.
the shift.
Yes, amount of shift of to the position. Yeah.
Surface to
Yep. Okay.
said that the conserved
Yes.
part D
Hmm?
is okay,
Yeah.
it's equal to that one,
Mhm.
but you said that sometimes
Yeah.
it can be simply rho times the Lorentz factor. Why did you say sometimes?
Yeah, because the low time is because this is depend on to the calculation, because if you see about for the equation, so this is root gamma g, but this is I think that as far this is specific for the code. I think the harm code is using for the d equals to rho ut, but the normal Valencia formula is using for the d, because this is rho time Lorentz factor, because it's alpha is coming from to the root minus d. You mentioned, I say that root minus d equals alpha root gamma.
Right.
So this is the alpha term is joined to here, then copied to here. It's compared to this one. So this is root minus d is changing for the root gamma.
So it depends on how alpha is really defined.
Yes. So if you including for the root minus d, conserved variable should be to the rho ut. So this is depend on the code. Okay. So what using for the determinant gamma or determinant g?
But in according to
Yeah.
the definition that you gave before to alpha and etc., and that
Yeah.
of course omega w,
Yeah.
then it's okay. This is always fulfilled.
Yes.
Right.
So this is I usually love to this kind of the case, because this is easy to recover to the special relativistic equation to compare it easy. Based on to the calculation, you can calculate for the determinant gamma numerically or determinant g the numerically. This is a different case, because you need additional numerical calculation you need to there. So this is it. Here I can just follow to the 3 plus 1 Valencia formula to way. This is one of the way to writing for the 3 plus 1 equation, formalism to equation. So this. So next, we are writing for the energy momentum tensor in terms of the quantities measured by the normal observer into 3 plus 1, the composition of the space-time. So first, this is the T mu nu. This is a perfect fluid. This is we have written here. Then we try to rewriting for this is the 4 component. This is U, S, and W component to here. So this is each U, W, S component mean to here. So U is this is 2 times up to the special component normal unit vector time to the energy momentum tensor. So this is the conserved energy density as a component of the energy momentum tensor, fully projected around the normal unit vector to the spatial hypersurface. It means the fully time component. Just consider about there. So Wij is this is gamma. It's going to there. Gamma is this is the projection tensor to get into here. So that this is spatial variant of the energy momentum tensor as a projection of the T into the space orthogonal to the n. So this is a time component. So completely fully a spatial component inside here. Then S is mixed up to the projection with this is the normal unit vector. This is the covariant 3 momentum density into the Eulerian frame as a mixed parallel transverse component of the T. So this is still we are writing for this is making for spatial. It means the 3 component. This is a time component. So it means this scalar component. Okay, so this is the 3 momentum tensor, including for the space and time is mixed up. So we are just decomposed to the what's the time component, what is the spatial component, and then this is mixed up. Okay. Yeah.
What happened with the decomposition when beta I is 0?
Beta I is a shift component. So just only we have the alpha, right? This is
the proper.
Yeah, this is a proper time, but still we are using for the same way. Yes, because the shift.
The energy moment tensor becomes diagonal in this case or not?
No, the energy momentum it doesn't affect up to the beta. Beta is just for the metric term. trick is just only for the shift vector. It's come up. So the energy momentum tensor doesn't include for the metric term. No, it doesn't include for the this beta.
The metric is present there, no, in the definition of the energy moment tensor.
This is yes. Yeah.
The metric is there.
This yes. Yeah. Okay. That's right. Yes. Sorry, I misunderstood. Yes, this is including for the yes the metric tensor. After that, I can say show about for the beta. Yes, this is including. So just dropping off to the beta. It's.
I suppose that when beta I is 0, the foliation is trivial because
Yeah.
you have the hypersurface, as happening, for instance, in Friedman model. We have the hypersurface, special hypersurface, and then we have a cosmic time.
Yeah.
That should be here defined by the alpha parameter. It seems that perhaps the energy moment tensor in this special case should become only with the
Diagonal term. Yes. But yeah, because the energy momentum tensor is a mix up to the energy density and the momentum term and to the.
This is the general form.
That yes.
Even for the perfect.
That yes. Yeah.
Okay, this is the general form.
Yeah.
But if you have symmetries in the metric,
Mm-hmm.
and then the energy moment tensor also feel
To get in here.
is affected by
Mhm.
the symmetry of the because in a different case you won't have a general relativist solution
Mhm.
because the geometry and the energy moment tensor
Mhm.
must have the same symmetry.
Okay. Yep.
Because you are U
Yes.
should be parallel to N.
Yeah, parallel to n.
Or
Yes.
in other words, perpendicular to the hypersurface.
Yes.
It's also perpendicular because
No, this is a perpendicular to the time. This is a fully spatial. Yes. Yeah.
hypersurface.
Yeah.
Ah,
Okay.
but still it's perpendicular, right? To a given.
Perpendicular to the time. That is every time. Yes. And then this can consider for the spatial component over time component.
Isn't the rest the local space?
Yes. Yes.
So it's
Yep.
fixed, yes. Orthogonal as well. It's
Mhm.
normal to time
Yep.
line.
Mhm.
Right.
So using for this analog, so we a little bit calculation to come to here. So the for velocity and the metric in its 3 decomposition form is also written to here. Then using for in this way, so that this energy momentum tensor also including for this calculation, writing for this kind of way. Then after rearranging for this term, we are comparable for this is the 3 component. We are rewriting for this one. So W mu nu is. We are here writing for yes 4-dimensional way because this is coming from this decomposition calculation to there. So rho h is the W square plus B mu plus the pressure term is here, and then S mu is also written here, and the U is written to like this. But here this is including for the for velocity, but so we don't have any time component. So we just written for this is the special component. The Wij is written here, and then this is the momentum density is written here, and the energy density is written here.
But it's free velocity.
Yeah, this is yes 3 velocity to like Ij to here.
No, yeah. But it's V, not U.
Yeah, not U. This is the B. Yeah. Okay, so using for now it's back to again for the. So this is the divergence, a full divergence of the symmetry of the rank 2 tensor. This is the energy momentum tensor the divergence. It's writing for this kind of equation. Then we are applying for the energy momentum tensor and using for the conservation of the energy and the momentum to get in for this equation like this. So I try to skip to the many details of the calculation. Unfortunately, this is the time is limited. And then applying for the composition form to the conservation of the momentum equation, it's just writing for this one. So there. And then a similar way using for the energy equation is obtained from this equation. Then we can rewrite it for the energy momentum tensor in the composition is like to here. So unfortunately, I don't have enough time to write, but maybe you can think or try to later to how to calculate this one to there. But I think this is only come for this the metric term. It's here. It's sorry, which this one? First equation. New lambda is a this is something I missed. I think that lambda is
Yes, because it's summing.
okay. Yes. Okay, now yes. A small sorry to this mistake today. So yeah.
This is a formulation for a perfect fluid.
Yep.
In the 3+1 decomposition.
Yes.
You cannot replace the energy moment tensor here by the energy moment tensor of the sum, for instance, perfect fluid plus an electromagnetic.
This is quite yes. We are trying to rewrite some yes. Here just is considered for the perfect fluid case. But if you think about for the non-perfect fluid, this decomposition is not satisfied sometimes. So we need rewriting for the equation anything over there. So this is one of the frontier to summarize.
I don't think you
Because the
can do
divergence
that.
of the energy moment tensor for the fluid in the presence of the electromagnetic field is not conserved. It's all right, and then the equation
It's not.
are modified in
Yeah.
some way.
Yes.
But it has been already written.
Or maybe you can think about for the energy momentum tensor is getting for the divergence part, and then plus the source term including for the magnetic or electric field
But
part.
then the source term must interact through the forces.
Yeah. But this is getting for the all yes. You mean this metric term or some additional thing? Yes, it's including here. Yes.
You try to decouple this.
Yeah.
You cannot.
Yes.
Not at this level. At least I can't. I would have to go back all
Yes.
in the equations.
So, yes.
In classical limit.
Yeah, I think it's a bit technical, but yeah.
It's very hard what you are suggesting.
But this is we can try. Of course, it's based on the four-dimensional equation. Try to consider for the this kind of decomposition, and then analytically you can calculate also possible to there. Or some assumption to the oil as a.
In any way, we may say that the first equation there
Yep.
minus the divergence, the forward divergence of the field. The first equation.
Oh, this equation, yes. Okay. Yeah. So this is a moment. We say this is a conservation of the momentum equation, and then this is a conservation of the energy equation to here. So still it's left over. It, but we can after that we try to rewrite in. After that we can get in for this kind of thing. Why I tried? Okay, yep.
So this is very nice because then you can solve everything in terms of S, U, and W.
That's right. Yep. So this is why we are writing for this kind of the more rewriting to this energy momentum tensor. So this is what is we know to this equation data onto there. So we also using for this is some the analysis there, and also rewriting for the source term in the energy equation part is also rewriting here. But this is also including for the extinctive curvature. It's including for this equation. But here we are assuming for the space-time the stationary. This is an extension curve.
Introduced there the string
How?
Because
It is, yeah, extrinsic curvature is one of the curvature to the space-time, something like this. This is relating from here, but yeah, this is, I forgot the exact one, I think. Yeah, at least this is need to calculate based on to the Einstein equation. If this is space-time is not stationary, we cannot decompose this kind of calculation. Sorry, I forgot this one.
okay, anyways,
Yeah.
you can define it
Yeah.
as in terms of W
Yes,
and
yeah.
recover the equations,
Mhm.
the equations on
Yeah.
the top, right? The two equations.
Yes.
The equation
So,
above. Okay.
yep. So at this, yeah, we are now it's trust about for the previous most of the paper is using for this kind of the equation. So I try to follow up this. It's missing or something over there. So maybe I to also. This is the 3+1 formula. So it's a hyperbolic system. We are thinking about for the now it's a conserved variable plus a flux plus the source term now. So the conserved variable is a hydro is using for the D or the Sj or tau. So D is we say this is a density related thing, and then Sj is we already written this is a momentum, and tau is we usually using for the energy density minus to the D. So this is numerically this is more stable than to the equation is a bit complicated, but this is numerically this is more easier to correct. Yep.
Just a small point.
Yes.
At this level,
Yes.
this description is general. I mean,
Mhm.
The fluid may have expansion,
Mhm.
may be contracting,
Yep.
may have rotation.
But it's
Mhm.
ideal.
But this is the yes.
For a
Viscosity.
perfect fluid,
Yep.
the kinematic parameters of the fluid may have rotation, shear.
That's a yes. This is yes. Yep.
Yeah.
Mhm.
Okay.
Fluid description. Everything is fluid. It expand or this is rotation. Info here.
There is no entropy production.
So okay. So this is a bit another is a differential formula. I think this is the font is the paper. It's something using for the source term. It's more one way is a simpler situation. Not simpler. This is one way before to calculate for this more the exchanging for there. But this is something. Yeah. This is same.
They are both completely equivalent.
Yeah, equivalent. Yes.
Right.
But also the some definition is a little bit different. So that we are using for the capital B. This is Bi is the alpha Bi minus the beta I.
Transport velocity.
Yes. But this is the font the paper usually using for the B tilde I. This is the Bi minus the beta I over alpha. So we are using for the mostly to the all the determinant of gamma, but here is using for the determinant G is including here. A little bit coming. One of the technique, same as to the Valencia formula. So this is recovering for the special relativity, the Newtonian limit. So I just skipping for this source term. It's just written for the simpler way. So here this is a full GR, but we also dropping after the shift vector equal to 0. So this is still including for the metric term into the source term and the determinant component also here. If consider for the Minkowski space-time, this is dropping down to the covariant and the contravariant is completely same, and then the equation is writing here. This is the same as the special relativity equation. No, special relativity hydrodynamic equation here. the further down we can consider for the Newtonian, this is removing for the relativistic connection, then we can rewrite in for this kind of equation. So this general relativity immediate equation is also recovering for the special relativity and Newtonian limit to there.
But could be
Yeah.
MHD as well.
Yeah, well, of course, this is MHD, it's same way.
Yeah. Now I see that you have
Yeah.
only P, you have dropped the terms.
Yeah.
Right.
Okay.
Right.
Sorry.
In the Minkowski case,
Yeah.
There is a contribution of the time derivative of the pressure.
Time derivative pressure.
That, of course, is missing the Newtonian case. Disappear because
Yes. Yep.
it is of the order 1 over c squared.
Yep.
It's not very clear from here,
Yep.
but there is a contribution. Do you have some interpretation for the why?
Here is a. But this is coming from to the.
It's the time
Yes.
derivative for P.
Yes. But
Time
only
derivative.
Minkowski case, not in the.
But yeah, this is a definition of the H. So H is enthalpy including for to the rest mass energy, internal energy, plus the pressure over to the density. This is just removing for to the after the this one because this is W equal to 1 because the Lorentz factor is dropping off. Then this pressure component it disappear.
You have neglected terms of 1 over c squared.
1 over c squared, yes. I think this this is not need to this kind of the definition. This is definition of to the enthalpy, relativity enthalpy or Newtonian enthalpy.
It's the same, Vladimir. It's there.
No, because you know that, for instance, in the Euler equation, the Newtonian equation, there is contribution of the gradient of the pressure, not of the time gradient of the pressure.
You mean
The
in
derivative, the
the
time
moment,
derivative of the pressure doesn't contribute.
you mean
in the
in the
Newtonian
momentum
level.
equation, but the energy equation,
But
it
it's the
is
pressure itself,
yeah,
not the derivative, the time derivative like that. The T of
yes, it appears in
Ah,
the energy
okay.
conservation equation, not in the momentum equation, but in the energy conservation equation, yes.
Yes, okay. This is okay. Yes.
Internal energy term.
Yeah. Momentum equation. Yes, we are
No.
dropping. Right.
Yes, doesn't. But
but in this term, when you obtain
there,
Yeah, I think this one and this one, right?
present here, no?
This is the present. Yes, a pressure term. It's the time derivative pressure, including for the enthalpy correction. But here is yes, we are dropping off to the pressure term.
in the
Yes.
momentum
Yeah.
equation, yeah, that's true.
Okay. The question.
Yes, you are recovering the particular cases, the special relativistic and Newtonian. But you should, if you are recovering the Newtonian case, you should recover the gravity term also, right?
Gravity term, yes, coming from to the yes, based on to the this is additional up to the Poisson equation. Yes. This is also coming from to the original the crystal symbol to also getting for to the some equation, but yeah.
I didn't see this.
Yeah.
Because the gravity is a source term of the Newtonian
Yes, but this is
equation. So how to recover this? You need to put by hand the gravity term as a source term?
yes, no, everything with the source term is external gravity case. This is we say a coupling for the Poisson equation type since we are directly recover for to the metric component. I think it's a crystal symbol to calculate for this kind of way.
No, but I think that we obtain it if you expand at first over the.
This is yes part of the
Newtonian
yeah.
gravitation.
Starting for to the yes.
Porque también because it is also como ser una fuente. Now said, it's not.
Okay.
Zush,
Yeah.
it's a little bit strange to me, this formulation. So
Yeah.
just to reinforce some points, the first equation
Yeah.
is the mass conservation equation.
Yeah.
That's
Mass conservation. Yeah.
the second equation.
Yeah. Momentum.
In any rectangle, in any box here, the second equation
Yeah.
is the conservation.
Yes, momentum conservation.
And the last equation is the energy conservation.
Yes, yes. Yeah. Okay. So this is the agent value to the characteristic speed. So the numerical scheme is based on the Riemann solver due to the local character of the hyperbolic system of the equation. I can explain to this Tuesday. Exponent degree the degeneracy and the complete set of the right agent value is vectorized exist. The above system is satisfied the definition of the hyperbolicity. So that this Jacobian is calculated here, and then the agent value to here. So this is it's the hydrodynamic case of the characteristic speed. It's making for to the entropy wave with the sound speed is correction to them. Then this is to inside to here. So this is a hydrodynamics case. We also recover to, after that, talk about the okay, so the special relativist limit along to the x direction, we are writing for the coupling with the trans to there. Then even for the pure 1D case, we are making for to the this constants. Then this is because to the Newtonian 1D case is how difference is coming from to this special relativity and the normal Newtonian case. Good point, of course. This is for the causality, equation state is sound cone. It's every time lie into the within the right cone. So we doesn't broken up to the causality. Right. This is important for the general relativity or special relativity also. Okay. So going to the 3+1 form of the general relativity MHD equation, again, using for the conserved equation, conserved energy density, it's written for the T mu nu, N mu N nu. It's including for to this term. So this is half E square plus B square, point flux term, and then this is E square. It's changing for the 1 plus B square because we are using for this E square is combined for the B square, and this will be B. This is a V cross B term because we are assuming for the ideal MHD equation. Then the 3 momentum density is also add to this contribution of the E cross B term, and then this is also dividing for this kind of way. Then the energy momentum tensor part or the spatial variant part is also including for the E and B term, and then this is also rewriting for this one. Here we are set up to the total pressure. This is including for to the gas pressure plus magnetic pressure contribution, both of including here. Okay, so this is our back geometry simulation code using for this 3+1 form of the geometry equation, hyperbolic system, and then this additional is coming from to the conservation. It's the magnetic field. This is coming for the induction equation. So important is that this induction equation B nu is also changing for to this the velocity over there.
But it's similar to Valencian.
Yeah, this is the Valencia based on the Valencia formula.
Right.
So this is also the right into here, and then source summit doesn't change, and then this is each component including for the magnetic field contribution. But here we are also trying to using for the small b, because to reducing for the memory, using for the all capital B to calculate for the all equation. So this is a bit complicated, but this is one of our way. Yeah.
You have introduced the electromagnetic field.
Yes.
In the same formulation.
The same formulation. Yeah.
Yes, but just to be clear, have you assumed that the energy moment tensor of the electromagnetic field is separately conserved or not?
This is the same. Of course, it's show about for the equation, This is an energy momentum tensor. All energy momentum tensor should be conserved.
Oh,
But
total energy
yes.
moment tensor.
It's conserved. Energy momentum tensor is dividing for the fluid part and to the electromagnetic part. So this is just the mix up to here.
Remember, he did this
Yes,
a
but
few
then the
slides.
divergence of the would come from the interaction.
This is similar to the Newtonian analog. Yeah. This is just only for the plasma. Yes, external field. Yes.
But
Yes.
it's coupled with the fluid.
Yes.
Yeah.
Separately done.
So like gravity.
This is yes, complete separate field. Yes. So also including for the formulation. Our GRMH simulation, because for the magnetic monopole control onto the AMR grid, we sometimes solving for the augmented Faraday law. This is getting for the normal Faraday law plus additional psi. This is the numerical scalar to give it to the this is a Faraday equation. Then this Faraday law is making for the additional contribution up to this is the equation, and then this is also solving for the additional phi. Then this is catch on for the then with the time the numerical. The diverse.
What is that for? How this cleaning?
Depend on to the this is kappa. Yes, this is a damping is a parameter. So how much you can. This is propagation and the damping term. So this is also arbitrarily we can choosing for this damping term is some number. Then this is how much affect. This is also need to some testing. This is similar to the artificial viscosity.
But this is for adaptive mesh refinement,
Yeah.
right?
Mm-hmm.
So I suppose that this is to correct for
Yeah, somewhere yes. Yeah.
yes,
Mm-hmm.
temperature effects this hypersurface when
Mm-hmm.
you divide it in smaller and smaller, right?
Yeah.
But how does it work?
But this is quite well work as far as I remember. Yes, because this is we number to here. We also anticipated the problems around the 10 to minus maximum is 10 to minus 3. Most of the region is 10 to minus 6 level. We can get in for the simulation. Yeah. But this is also the one of the technique. Now we are everything switching for the constraint transport scheme. But this is one of the way But we are at
This is cooking.
yes, this is about cooking. Yes.
Yeah, pure cooking.
Yep.
Right?
Then of course this is additional equation. It's getting further more complicated. So that maybe see about. So both is hand side is propagation. So total 7 waves we can include in here.
Entropy wave is essentially noise.
But this is the contact discontinuity.
I beg your pardon?
Contact discontinuity. Yes, contact discontinuity. Yeah, this is not noise. This is actual.
Numerical noise. And sometimes because it's just to deal with this neighbor.
Okay.
No,
Maybe.
Information in the real fluid.
Wave, right? This is a
Not necessarily,
Necessarily.
but
The
it's
production of
related
the
with
heat production,
with
the-
discontinuity.
The
Like shocks of Newtonian numerical codes, right?
But this is explain why you are associate this to the noise when you have, for instance, non-physical discontinuities.
You have physical discontinuities in real
When you have
quantum
shocks,
physics.
but you are not describing shocks.
Yeah.
yeah. This is a not similar.
Yeah.
Okay.
Okay?
Hmm?
And this is not the Ohm's law doesn't
Yeah.
play any role here.
This is
The
Ah.
relativistic Ohm's law.
usually we are using for to the some simplified dispersion relation to get in for the this kind of the way. But more diffusive behavior. This is the numerical.
Telling that there is an overestimate of the wave speed
Yes.
of the frame. This is experimental. This is obtained in lab or
Uh,
not? How you do that?
to describe the Riemann problem.
Problem, yeah.
Right? We are now he's discussing how we solve the GRMAGD equations numerically.
Yes.
Remember, in the classical limit, all these characteristics, these waves had exact solutions. But now,
Yeah.
because of that particle, etc., you have to solve numerically for. These are the Riemann solver in the general relativistic MAGT approach. Right?
Okay. So this is yes, yeah. I just a little bit jump into the how to part of the numerical relativity or the general relativity, how to get in from here to include here.
It is really
Yeah.
complicated.
Okay. So so this is a numerical simulation. Do that. The velocity and the magnetic field. Two from to the conserved variable using for this is the case. Now, yeah. So the forward transformation put the primitive variable to the conserved variables as a closed form solution. But inversion is a transformation, is a calculation of this conserved variable to get in for each density or velocity or gas pressure. It's not straightforward. So we need some numerical calculation need to there. Then usually we are using for the Newton-Raphson method, but now the recent one of the paper using for the deep. We need some numerical method to solving for the nonlinear equation to catch up for this root finder type thing to get in for what's the density from the coupling for this conserved variables. This is one of the yeah.
What fraction of the significant fraction of the code spent on the inversion procedure?
The fraction. So much different way to calculate it, getting for the correct answer. Sometimes it fail, we can return back, and then we can correction of the some energy, the conserved variable, try to again. But if it fail, then we can try to another way, or fail, maybe we can recover another things. So it's a quite a long time, but yes. So there. Okay. Yeah.
Just a very naive question.
Yes.
Because all of the time we will convert the conservative variables to primitive to
Yeah.
solve the Riemann solver
Yeah.
because of the stability of the numerical solution.
Mm-hmm.
My point is, in another words, it's possible to solve the Riemann solver. It's possible to solve the Riemann problem using the conservative.
The quantity. No, I think.
Since it's too costly to solve
Yeah.
to solve the GRMD equations because of this conversion between the conservative to primitive. Why
Are there any other methods?
Yes.
So yes, yeah.
To solve the Riemann solver
Yeah.
directly using the.
Or to avoid the Riemann problem?
Yes.
As far as I know, no, nothing. To
For
the,
GRMATD.
for GRMATD, every time we try to avoid as much as the minimum this C2P calculation. Yeah, this is yeah.
But if I want to try to solve the Riemann problem using just the conservative variations,
Yeah.
is it possible or not?
Currently, my feeling is no. Not exactly you can catch up for the correct answer because if you calculate for this wave speed, you need also calculate for some information for some density or some other velocity. Quite hard point to get in for the based on this conservative variable to get in for there. So important velocity and the pressure. These two variables quite hard to get. If you get in for the velocity, easy to get in for the density. Magnetic field is just skipped. So that this velocity and the pressure is
Much harder than
much.
use the Newton-Raphson method to solve the
Yeah.
problem too.
That yes, yeah.
Not to tell when
Not.
we include also radiative cooling implicitly, non-equilibrium radiative
Mhm. Yeah, this is yes.
Forget it.
Or maybe you can use GPU just for
Yeah.
conversion.
So okay, this is here. So is another tips is using for the horizon penetrating form of the black hole metric. So the Boyer-Likes coordinate of the black hole metric has a coordinate singularity at the black hole event horizon radius. So the metric term is divergence. So we cannot solve in for the numerically as event horizon. So we should set the inner boundary is outside the black hole event horizon. So black hole event near the event horizon is the most important or most interesting point of the numerically try to solve. But this is a Boyer-Likes coordinate doesn't allow to doing for the to the simulation in this region. So we can choose for the particular observer, such a coordinate singularity can be removed. Such a black hole metric form is so-called the horizon penetrating form. In the Schwarzschild black hole, typically the Eddington-Finkelson is a coordinate system, or Ramirez coordinate system is also making for the horizon penetrating form. Or in the Kerr black hole case, the Cargill coordinate is one of the horizon penetrating form over there. We have found the general way to making for the horizon penetrating form onto the special relativist spherical metric case, but I couldn't find any solution to any axiometric metric type. In this case, mostly the axiometric metric, it's case by case you need making for the horizon penetrating because the whereas happen for the coordinate singularity and then try to change in for the some coordinate transform to making for the avoid this coordinate singularity something. But this is a bit over to this one.
In limit coordinates,
Yeah.
in Schwarzschild black hole, this should be very simple. No problem.
Yes.
If you consider limit coordinates,
Yep.
and then the shift parameter
Yep.
at I is 0.
Yes.
Because
Yes. No. Nothing. Yes. Yeah. So I know to the general form of the spherical symmetric any spherical symmetric metric case to for this horizon penetrating form. So I can like this Dilaton black hole simulation. I say sure about for the and transform to the horizon penetrating form to doing for the simulation.
But then the metric is time dependent.
Yeah.
Because we have this one that is free falling.
Yeah, free falling. This is the observer. Yes.
But then this creates some problem to.
No, it's because the space time is everything is same, but the problem for the where is locating for the time. We need after the simulation time up state, and then we can get in for the position. Then if you get in for the information passing to the general relativity radiation calculation, we sometimes convert to the Boyer-Likes coordinate. So this is more the transformable information to calculate for the radiation.
But then the boundary condition is within the horizon.
That within the horizon. Yep. So this is why we are choosing for this kind of horizon painting form. So other questions? Yes. Yeah.
So how do you do with your Dilaton black holes?
Yeah.
What coordinates do you use for your Dilaton?
This is we are writing for the. I haven't writing for the papers, but we making for the general form to transforming for the normal Boyer-Nichols coordinate to changing for to the horizon penetrating form to the similar to the this laminar coordinate absent. Yeah, if you are interested, I can give to the information. Okay, so this is a Cargill coordinate. So, this is in the spherical coordinate. This is written for the GTT term, GTR, GT phi, and then to the GRR, GR phi, and the G theta, G phi phi. So it's a bit an additional component coming to here, but this is avoiding for to the coordinate singularity. And one of the notes is the original Cargill coordinate is written into the Cartesian coordinate. So if you back to the original paper, you see about for the Cartesian coordinate to written for the Cargill coordinate. Okay, so this is a Cargill coordinate. Of course, we are writing for the 3+1 decomposition in the metric. So we are writing for the alpha and the beta, just using for the shift vector as r, because this is time-like things. So position is shifting to the r direction. And then this is a 3 metric component to there. So this is, if you return back to the 4 metric, you can calculate this kind of the relationship there. Okay, so this is one of the comparison with the Cargill metric. We are also writing for the Carl metric. So Carl metric it's rather simpler. Alpha and the beta is phi, and then to the GRR something like this. So this is also if you want to get in for the 4 metric, you can calculate for this kind of thing also there. So this is just a gift to the. I try to say a little bit about for the numerical test. So various set of the numerical tests for the validate for the code accuracy and to perform the special relativist MHD and the general relativist MHD. So the special relativist shock tube test is also using for the special relativity. We know about for the now its exact solution. And then to the magnetic loop advance is also checking for the diversity problem, even for the special relativist MHD case. Brass wave is the propagation test is with the magnetic field is one of the well done is a brass wave test just compared to the previous simulation case. Jet propagation also everyone is trying to do. We try to also sometimes case, but this is a bit complicated. Magnetic reconnection also checking for the resistivities, especially relativistic resistive MHD called C. So we can do that. Then this is red one is we can write in for the pure general relativistic test. So one is a spherical Bondi accretion test. This is general relativistic hydrodynamics. And then stationary hydrodynamic torus. This is also general relativity hydrodynamics. And then recently is a Komisarov also proposed the magnetized torus with a toroidal magnetic field. This is the pure general MHD equivalent as a torus structure. But this is sorting for the 2D. But this is also one of the new tests to do for GRMHD simulation code.
But only 2D.
Yep. So this is the Bondi accretion. So now I show about the one of the simulation result. This is a Bondi accretion is an analytical solution of the spherical accretion flow onto the Chevalier black hole. It's see about for the Hori et al. 1984. The paper is already written. Yeah. Then this is a pure. This is one of the simulation we can done. I think this is already. This is a Chevalier coordinate. Yes, doing for this. Then is a pure radiation. Radial magnetic field does not affect the flow of the structure. So we try to do field also put on there. Then try to get to similar this. Then this is also we know to the analytical solution. So that we making for to the convergence also test using for this Bondi accretion test also. Okay.
The
Yeah.
diagram,
Yeah.
this one, the one able.
This one?
Yes.
This is a 3-dimensional test. We are doing for the 3-dimensional at the Bondi accretion test using for the now show about for the density today. Okay. So this is a stationary. Yeah.
In the case of a fully radial magnetic field,
Yes.
doesn't affect the flow structure.
If
The solution, all
it's a this is a
Gauss law is satisfied in this case.
no it's a
We have a radial, pure radial.
this is pure radial. This is the solution to pure radial.
The intelligence of B is different from 0.
Yeah,
Yes.
you have to,
Yes.
you have,
Yeah.
It's an ideal.
Yes. Okay. So this is the stationary hydrodynamic torus. So there are several solutions for the stationary hydroequivalent torus with the constant or different angular momentum case. Is famous is the Fishman-Moncrief in 1976. Hore also give to the 1984 the paper. We are using for the Fontaine torus in 2002 paper because this is more general way to including for the metric component. Because of the Fishman-Moncrief is specified for the parametric case to get in for the solution over there. But Fontaine the paper is using for the more general way. So we are showing about this is one of the Fontaine torus station. This is the initial setup, and then this is the take 150 times something the simulation. And also we are see about for some accuracy of the code. Also try to testing for the stationary hydrodynamic torus case. So it's a little bit talk about for the adaptive mesh. So because of we are based on our GRMHD code, the back code using for the adaptive mesh is we can divide to the is a block. So space filling curve is also uniquely done over the block integration, and the load balance is done by this filling curve. So this is the idea. It's just only for the 1 point. If you are interested, you can try to make an additional level. We divide to the 4. Then if you have a more interest, maybe we can divide to the 4 to 4. This is a fairly standard way to the parameter to the Asina++. This is quite advanced to the AMR. So this is one of the our simulation doing for the AMR performed to the general relativist hydrodynamics. Here we consider for recoiling black hole. Recoiling black hole means to the initially we can set up the black hole and the accretion torus, but we can put onto the shifted or the kick to the one direction. Then this one direction making for this kind of the shifted about for the rotation, and then making for this kind of the spiral shock is the type of the case. So now we are writing for this is shock position is how to get in for this shock based on the simulation. Is that now MR is a functional is work is that this spiral shock region is nicely follow up to the MR grid over there.
This is important for interacting
Yep.
black holes.
Yes. So this is the AMR grid. So if you a little bit hard to say, but the AMR is a higher refinement block. It's follow up for this shock structure over there.
This is adaptive.
This is adaptive.
Fixed?
Adaptive. Yeah. Okay. So it's a little bit to talk about for the coupling with the GRRT code. So radiation transfer calculation using for the ray tracing method, including for the thermal and non-thermal radiation process, and the fully coupled with the backcode onto the my lysine code. This is the major pipeline. So the simulation data is given to the radiation transfer, and also that we assuming for the physical model of the emission. This is also returned back to the simulation data to get in for the radiation transfer. Then we are making for the different time of the radiation transfer image to the different time scale. Then this is combined to the multi-image. We can make it for the movies, and then integrated over the all image. We may also contain about the light curve, or one stack image also integrate everything, making for the spectra, something like this. So this is a completely post-process calculation. We need the frequency dumping for the simulation data. Then each one data is making for the one each image. So this is the testing for this recording black hole 3D case. We are making for the total intensity, see about for the 60 degree over there. So based on the 3D one, and they only consider the thermal radiation, and because this is non-magnetic field because of the hydrodynamic simulation, then we can calculate all performed the multiple of the band frequency, like the radio, optical, infrared, or X-ray, and dependent here. So this is the light curve of the total flux, depend on the inclination. You see over something different over there.
So
Yeah.
just for curiosity,
Yeah.
in case of the adaptive mesh refinement, what is the condition to refine the?
Yes, this is a big point over there. In this case, we are doing for the two way. One is Ronald scheme we can consider. This is the second the derivative of the some the quantity like this density, pressure, or some velocity. It's some threshold become high. We can make it for the reconstruct. Yeah, it's making for the additional level. Or in this case, we also try to make it for the shock capturing the scheme to try to looking for the where the shock is happened to there. Then follow up to this shock structure, we can make it for the line adaptively making for the higher refinement.
But in this case, you can impose this.
Yes. So first we can any kind of threshold. It's over to some threshold. You can make it for the refinement, but this threshold is written for the some the second derivative or something, or some specified way, or we can force to something.
Yeah, just
This is like this. Yeah.
In classical codes.
Yeah.
Classical
So
adaptive measurement.
yeah. So this is our case. It's just using for the two-way. So but both of cases it's very similar result in this case for the this recording case over there. Okay, so this is the summary. So almost time. So the geometric equations are composed by the conserved law of the density and energy momenta coupling with the Maxwell equation. Geometric equation describing its dynamics in the 4D curved space, and then the solving for the geometric equation is numerically we should use it for the 3+1 formalism to decompose the time and space. Then the Valencia formula is a well-used 3+1 form of the geometric simulation and equation, and then relative symmetry simulation needs additional numerical calculation of the conserved variable to the primitive variable. This is quite a new point for the relativistic case. Okay, so this is today's part.